This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Ascii, Institute of Aeronautical Engineering. Today I am going to take the topic Instruction Set of 8086, under which I am going to discuss Arithmetic and Logical Instructions. The slides are prepared by referring the textbook titled Advanced Microprocessor and Peripherals, authors A.K. Ray and K.M. Urchandi, McGraw-Hill Publications. Arithmetic instructions are used to perform arithmetic operations like addition, subtraction, multiplication, division, etc. Following are the instructions under this group. Instructions to perform addition: add ADD, add along with carry ADC, increment INC, Ascii Adjust after addition AAA, decimal adjust after addition DAA. After that, we will discuss the instructions to perform subtraction: SUB subtraction, SBB subtraction with borrow, DEC decrement, negate NEG, compare CMC, Ascii Adjust after subtraction AAS, decimal adjust after subtraction DAS. The instructions to perform multiplication are unsigned multiplication MUL, signed multiplication IMUL, Ascii Adjust after multiplication AAM. Instructions to perform division are unsigned division DIV, signed division IDIV, Ascii Adjust before division AAD. The last category related to arithmetic operations are instructions to conversion of data: convert byte to word CBW, convert word to double word CWD. First, we will say the instructions related to addition ADD. This instruction is used to add the provided byte to byte or word to word. The syntax of the instruction is ADD destination comma source. Here, the destination can be a memory or a register, whereas the source can be a memory location, register, or immediate data. The instruction ADD instruction add the content of source content along with a destination contents, and the result will be stored again in the destination. After executing the add instruction, the various flags will be affected are auxiliary flag, carry flag, overflow flag, parity flag, sign flag, and jet flag. Few example related to add instruction is add AL comma BL. Here the contents of AL register will be added with the contents of BL register. The resulting sum will be exist in AL register. Add CL comma 14H. This is example for adding immediate data to a register. Here the CL register contents added with a 14H immediate data, and the result will be stored in CL register. Add in brackets BX comma AL. Whenever you have placed brackets, this will refers to a memory location. The contents of AL register will be added to the contents of the memory location whose address is specified in BX register. Again, the result will be stored into the same memory location. Add BX comma in brackets SI. Here, the source data is a memory location content whose address is specified in SI register. So, the contents of the memory location whose address is in SI register will be added with BX register content, and the result will be stored in BX. For this instruction, the source and the destination should be of same size. Either it is 8-bit by 8-bit or 16 by 16-bit addition is possible. Both source and destination cannot be memory locations. The next instruction is ADC, add along with carry. This instruction is used to add along with carry. The syntax of the instruction is ADC, destination comma source. Here, the destination can be a memory location or a register, whereas the source can be a memory location or a register or an immediate data, but both source and destination cannot be memory location, and the size of the source and destination will be always same. The ADC instruction functionality is the source contents are added with a destination content along with the carry flag. The result will be stored in a destination. The various flags will be affected are listed here. Few examples related to ADC instruction are ADC, AL, BL. Here, the contents of BL register will be added to AL register along with a carry flag, and the result will be stored in AL register. ADC, CL, 14H. Here, the contents of CL register will be added with the immediate data, that is 14H, along with the carry flag, and the result will be stored in CL register. ADC in brackets BX, AL. Here, the contents of AL register will be added to the memory location contents whose address is specified in BX register along with the carry flag, and the result will be stored in the memory location whose address is specified in BX register. Next example is ADC BX, in brackets SI. Here, the source content is a memory location content. So, the contents of the memory location whose address is specified in SI register will be added to BX register contents along with the carry flag, and the result will be stored in BX register. If the carry flag is 0, then ADC instruction and ADD instruction will perform same. The next instruction is Increment Inc. This instruction is used to increment the provided byte or word by 1. The syntax of the instruction is INC, DST, destination. Here it is a one operand instruction. The destination can be a memory location or a register. The INC instruction functionality is this instruction adds 1 to the register or memory location, and the result will be stored in destination register. The functionality we can write as destination contents plus 1 will be stored again in destination. The INC instruction is same as that of add destination, 01H. So this instruction will perform the addition operation between the destination contents along added with the 1, and the result will be stored in the destination. The example related to INC instruction are INC AL. The AL register contents will be incremented by 1, and the result will be stored in AL register. Increment CX. Here the source size is 16-bit size. The CX register contents will be added with 1, and the result will be stored in CX register. Increment in brackets BX. Here the contents of memory location whose address is specified in BX register will be added with 1, and the result will be stored into the same memory location. Similarly, INC in brackets SI. Here the source data is a memory location contents. So here the contents of SI register memory location whose address is specified in SI register will be added with 1, and the result will be directed to the memory location whose address is specified in BX register. The next instructions related to addition operation is AAA stands for Ascii Adjust after addition. This instruction we have to perform after addition instruction. After addition, the result should be exist in AL register. Then only we can use AAA instruction. This instruction is used to adjust ASCII after addition. The syntax of the instruction is AAA. So here it is 0 operand instruction. So the implicit operand is AL. So whatever the contents of AL register is there, this will be in form of unpacked BCD that will be converted into a valid unpacked BCD value. So this instruction adjusts the sum of two unpacked BCD values to create an valid unpacked BCD result. In this instruction, AL register is called as implied source and destination operand. So after converting into ASCII, the result again we can see in AL register. It is an implicit operand. The flags which will be affected for AAA instruction are auxiliary flag and carry flag. Example, move AL comma 31H, 33H. So AL content is 33H, add AL comma 39H. So AL is equivalent to 33H plus 39H. So if we add 33 plus 39, 9 plus 3, it is equivalent to 12 in decimal. In hexadecimal, it is equivalent to 6. 3 plus 3 will give 6C. So after addition, this 6C will be exist in AL register. So whatever the AL register contents are there, this will be converted into unpacked BCD with for valid format. So that will call as ASCII Adjust after addition. After executing AAA instruction, the AL contents will equivalent to 02H and AH contents is equivalent to 01H. Now we will see how this AAA instruction will work. So that means converting in this example, the 6C after executing AA instruction, it is results to 02H in AL register, 01H in AH register. So now we will see in detail description how this instruction will be executed. We will take with respect to few examples. The various steps which will be takes place for executing AAA instruction are: in step 1, clear AH register. Step 2, clear the upper nibble of AL register. So as AL register is a 8-bit register, so the bits from 0 to 3 are lower nibble, the bits from 4 to 7 are higher nibble. So the upper nibble, that is from bits 4 to bit 7, will be clear. Then examine the lower nibble of AL register, that is bit 0 to bit 3. If the lower nibble of AL register is greater than 9, as it is not a valid BCD, we have to add 06 to the AL register contents as well as increment AH register. Next, if lower nibble of AL register is less than or equivalent to 9, as it is a valid BCD number, no changes will be takes place for AL register and AH register. Now we will see with respect to few example. Assuming after addition, the AL register content is 6CH. Now we will see how this AA instruction will work for this result. So in the first step, we have to clear AH register, that is AH register is equivalent to 00H. Next, the AL register, the upper nibble will be checked. So here the lower nibble is C, upper nibble is 6. In this step, this 6 will be cleared. So after the second step, we will get the AL register contents as 0CH. Next, we have to examine the lower nibble. In this case, the lower nibble is C, as this one is greater than 9. As this C is greater than 9, it is not a valid BCD number. So we have to add 06 for the AL register. So now AL register contents we are having are 0C. For this we have to add 06H. The data here it is in hexadecimal format. C, it is in hexadecimal. Equivalent decimal is 12. 12 plus 2, 18. 12 plus 2, 12 plus 6, it is 18. It is in decimal format. In the hexadecimal, it will give us as 12H. It will give us as 12H. So this 2 will be moved to AL register. Whatever one is there, this will be moved to AH register. That is, AH contents will be incremented by 1. So now we'll get AH contents as 01H. So after executing AAA instruction, before that AL register contents are 6CH. After AAA instruction, the AL register contents are 02H. AH contents are 01H. Now we will move to another example where assuming the result after addition, the AL register content is 69H. So for this case, how this AAA instruction will work? As we know, the first step is clearing AH register. So AH is equivalent to 00H. Then we have to examine the lower nibble of AL register. The lower nibble of AL register is 9, upper nibble is 6. In this step, first we have to clear upper nibble before checking the lower nibble. So after this, the AL register, by clearing the upper nibble, we will get the AL register content as 09H. Now examine the lower nibble. In the lower nibble of AL register, the contents of this one is satisfying less than or equivalent to 9, as it is a valid BCD number. So no need to alter AH contents and AL contents. As we have cleared earlier AH register, so this will be retained as 00H and AL content is equivalent to 09H. So if AL register content after addition is 69H, after executing AAA instruction, the AL contents is equivalent to 09H and AH contents is equivalent to 00H. Now I will take a third example where assuming the result after addition instruction which are exist in AL register is equivalent to D9H. As per AA instruction, the first step, clear AH register. So AH register is equivalent to 00H. Next step is, for AL register, we have to clear the upper nibble. So in this case, the upper nibble is D. So this will be cleared to 0. So now we will get 09H as AL register. Next, we have to examine the lower nibble of AL register. As this lower nibble of AL register is a valid BCD number and it is less than or equivalent to 9. So don't alter AH or AL register contents. So after AAA instruction, AH contents is equivalent to 00H and AL contents is equivalent to 09H. So here we consider the input AL is equivalent to D9H. After AAA instruction, the AH contents is equivalent to 00H and AL content is equivalent to 09H. 09H. Now we'll see the last example related to AA instruction. Assuming after addition, the sum is AB which is exist in AL register. So how this AA instruction will perform is, first it will clear AH register. So you will get AH is equivalent to 00H. Then examine the lower nibble and upper nibble. So before that, first we have to clear the upper nibble. So the upper nibble is A. This will be cleared to 0. After that, we will get the AL register content as 0BH. Then examine the lower nibble. In this case, the lower nibble is 0BH, which is not a valid number and it is satisfying the condition greater than 9. So 06 we have to add to AL register. Now the AL register content is 0BH. For this we have to add 06H. B plus 6. B in decimal equivalent is 11. 11 plus 6, it is 17. It is in decimal. So B, which is equivalent to 11 in decimal. For this we are going to add 6. That will produce 17 as output in the decimal format. As it will store in the hexadecimal, it is equivalent to 11H. So you'll get 11H. This one will be moved to AL register. This one will be moved to AH register. That is, AH contents will be incremented by 1. So after executing the AAA instruction, the AH contents will become 01H, 01H, and AL register content is equivalent to 01H. So in this example, we are considered the result which is in AL register is equivalent to ABH. After executing AAA instruction, we got AL register content is equivalent to 01H and AH content is also equivalent to 01H. So these are the instructions related to addition operation. Now we will move to the instruction. One more. The next instruction is DAA. DAA stands for Decimal Adjust After Addition. This instruction is also we have to execute after addition instruction. After addition, the result should exist in AL register. So as AL register is a default register, we can take that one as implicit operand or implicit register. The DAA instruction is to adjust the decimal after the addition operation. The syntax of the instruction is DAA. It is zero operand instruction. The DAA instruction adjusts the sum of two packed BCD numbers to create a valid packed BCD number. So if you have any invalid BCD numbers, that will be converted into valid BCD numbers. AL register is the implied source and destination operand for this instruction. The flags affected after executing DAA instruction are auxiliary flag and carry flag. Few example we will take. First we are moving AL register with 33H. Add AL comma 39H. So 33 will be added with 39H. It is a hexadecimal operation. 3 plus 9 in decimal it is equivalent to 12. In hexadecimal it will give us C. 3 plus 3 6. Both in decimal and hexadecimal it is 6. So after addition we are going to get the AL register content is equivalent to 6CH. After performing DAA instruction decimal adjust after addition, the AL register contents, that is 6CH, will be converted into 72H. Now we will see how this DAA instruction will work. First we will describe what are the various steps we will be having for this DAA instruction. Then we will illustrate with respect to few examples how this DAA instruction will work. First we have to examine the lower nibble of AL register. If lower nibble of AL register is greater than 9, add 06 to AL register contents. If the lower nibble of AL register is less than or equivalent to 9, don't alter the contents. We'll move to step 2. In the step 2, we have to check the upper nibble of AL register. If the upper nibble is not a valid BCD number, that means if it is greater than 9, add 60H per AL register contents. If it is a valid number, that is the upper nibble of AL register is less than or equivalent to 9, don't alter the contents of AL register. Now we will see with respect to few examples. I am taking the examples which were considered for AA instruction. The same values I am considering for illustrating the DAA instruction. Let us assume after addition, the sum which is produced in the AL register is 6CH. Now we will see how this DAA instruction will function for this particular case. So now here we are having AL is equivalent to 6CH. In the first step, it is going to examine the lower nibble. As this lower nibble is greater than 9, as this lower nibble is not a valid BCD number, so we have to add 06 to AL register contents. So add 06 to AL register contents. Now we are having a 6CH in the AL register contents, for which we are going to add 06H. C is C plus 6. It is hexadecimal operation. C is 12 in the decimal. 12 plus 6, 18 in the decimal. 18 equivalent in the hexadecimal is equivalent to 12H. So now we will get this one as 2. Carry is 1. Next, 1 plus 6 plus 0, it is going to produce 7 to H. This is the result after first step. In the second step, we have to take the AL register for checking the upper nibble. So in this particular example, the AL register, the upper nibble is less than or equivalent to 9. That is, it is a valid BCD number. Don't alter this content. So the result is AL register is equivalent to 72H. So now we have considered the AL register content as 6CH. After DAA instruction, the AL register contents is equivalent to 72H. Now we'll move to the next example, where we are considering after addition, assume the AL register content is equivalent to 69H. We will see how this DAA instruction will work. So now here the AL register contents are 69H. In the first step, we have to examine the lower nibble. As the lower nibble is a 9, it is a valid BCD number. As it is less than or equivalent to 9, don't alter the content of AL register. So now after the first step, the AL register contents will remain same, that is 69H. The second step is again take the AL register contents, examine for upper nibble. In this case, the upper nibble is 6. As it is a valid BCD number and it is less than or equivalent to 9, don't alter the contents of AL register. So the result after the DAA instruction for this case is AL is equivalent to 69H. So in this example, we have considered AL register is equivalent to 69H. After DAA instruction, the AL register contents are remain same, as it is a valid BCD number in both upper nibble and lower nibble. Now we will move to the third example, where we are considering the result produced after addition in the AL register is equivalent to D9H. Now we will see how this DAA instruction will work. The result which is there in AL register is D9H. First examine the lower nibble. As this lower nibble is a valid BCD number, as it is less than or equivalent to 9, don't alter the contents of AL register. So after the first step, the AL register contents will remain same, that is D9H. Now examine the upper nibble. Now the upper nibble in this case is D. As this D is greater than 9, as it is not a valid BCD number, we have to add 60 to this AL register contents. Now AL register content is D9H. Now we are going to add 60 to this. We are going to add 60 to this. 9 plus 0, 9. D plus 6 in the hexadecimal addition. So if you are, otherwise we are going to convert in the decimal. First D equivalent is 13. 13 decimal plus 6 decimal, which will give 19 decimal. 19 decimal in the hexadecimal is used as 13H. So 1 will be moved to AH register. 39 will be placed in AL register. So after the DAA instruction, AL register content is equivalent to 39H. This will be moved to AH register. Now we will take one more example, where we are considering after addition, the result which is produced in AL register is equivalent to ABH. Here first we have to examine the lower nibble. In this example, the lower nibble is B, which is greater than 9, as it is not a valid BCD number. So we have to add 06 to AL register contents. This is hexadecimal addition operation. B plus 6. B in the decimal equivalent is 11. 11 plus 6, which is 17 in the decimal. In the hexadecimal, it is equivalent to 11H. 1 carry. A plus 1 is B. B plus 0 is B. So after first step, we will get AL register content is B1H. Now we will move to the second step, where we will examine the upper nibble after completing the first step for DA instruction. The upper nibble is, in this case, it is not a valid BCD number, as it is greater than 9. We have to add plus 60 for this AL register contents. 1 plus 0 is 1. B plus 6. B equivalent is 11. 11 plus 6, it is 17 in the decimal. In the hexadecimal, it will use as 11H. This 11 will be moved to AL register. 1 will be moved to AH register. So what is AL register contents we will get is 11H. Now we will move to the instructions related to subtraction. First instruction under this category is SUB. This instruction is used to subtract the byte from a byte or word from a word. The syntax of the instruction is SUB, destination comma source. The destination can be a memory location or a register, whereas the source can be a memory location or a register or an immediate data. Here the source and the destination cannot be memory location, and the size of the source and destination should be same. That means we can subtract a byte from a byte, otherwise word from a word. The functionality of SUB instruction as follows. The source contents are subtracted from the destination contents and the result will be placed in destination. The flags will be affected after SUB instruction of AF, CF, OF, PF, SF and ZF. Auxiliary flag, carry flag, overflow flag, parity flag, sign flag and zero flag. Few examples for SUB instruction are SUB AL, AL, BL. So what this instruction will do? The AL contents are subtracted with BL contents and the result will be stored in AL register. SUB CL, 14H. Here the contents of 14H are subtracted from CL register and the result will be stored in CL register. Next, SUB in brackets BX, AL. Here the source is a register and the destination is a memory location. So the contents of AL register are subtracted from the memory contents whose address is specified in BX register. The difference in these two values will be stored into the memory location which is pointed by BX register. One more example, SUB BX, in brackets SI. So here the source is a memory location contents whose address is specified in SI register. These contents are subtracted from BX register and the result will be stored in BX register. The next instruction is SBB. SBB stands for subtraction with borrow. This instruction is used to perform subtraction with a borrow. So there is no separate flag for borrow. Either it is addition or subtraction. We are going to take the reference is a carry flag. The syntax of the instruction is SBB, destination, source, where the destination can be a memory location or a register, whereas the source can be a memory location or a register or an immediate data. The source and destination are of same size, that is byte to byte or word to word is allowed. The both source and destination cannot be memory locations. The functionality of SBB instruction is the source contents are subtracted from destination contents along with carry flag and the result will be moved to destination. The various flags will be affected after SBB instruction are auxiliary flag, carry flag, overflow flag, parity flag, sign flag and gyro flag. Few example for SBB instruction are SBB AL, BL. So this instruction will subtract the BL register contents from AL register contents along with carry flag and the result will be moved to AL register. SBB CL, 14H. Here the 14H contents are subtracted from CL register along with the carry flag and the result will be moved to CL register. SBB in brackets BX, AL. Here the contents of AL register are subtracted from memory contents whose address is specified in BX register along with the carry flag and the difference we can store in memory location which is pointed by BX register. SBB BX, in brackets SI. So here the source content is a memory location contents whose address is specified in SI register. These contents are subtracted from BX register along with the carry flag and the result will be moved to BX register. The next instruction is DEC for decrement. This instruction is used to decrement provided byte or word by 1. The syntax of the instruction is DEC destination. It is a one operand instruction. The destination can be a memory location or a register. After performing the decrement, again the result you can see in the same operand. The functionality of DEC instruction is it will subtract 1 from the register or memory location which is specified. The functionality we can write as the destination contents minus 1 will be stored in destination. It is same as that of SUB destination, 01H. Example for this case is decrement AL. So it is same as that of performing 1 is subtracted from AL and it will be stored in AL register. Decrement CX. So here the CX are register contents are subtracted with 1 and the result will be stored in CX register. Decrement in brackets BX. Here the contents are memory location contents whose address is pointed by BX register that will be subtracted with 1 and the result will be stored into the memory location. Decrement in brackets SI. So this instruction will subtract 1 from the memory contents whose address is pointed by SI register and the result will be stored into the same memory location which is pointed by SI register. The next instruction is NEG. It is negate instruction. It is used for negate each bit of the provided byte or word and add 1. It is same as that of performing the 2's complement on the operand. The syntax of the instruction is NEG destination. The destination can be a memory location or a register. So it is also a one operand instruction where the contents of operand 1 will be performed with the 2's complement method and the result will be can see in the destination itself. So this instruction functionality it is same as that of subtraction of the destination contents from the 0. It is same as performing the 2's complement. So again the result will be moved into destination. The syntax of the instruction, the examples for negate instruction are NEG AL. Here the AL register contents are subtracted from 0 and the result will be stored in AL register. Negate CX. Here the CX register contents are subtracted from 0 and the result will be moved into CX register. Negate in brackets BX. Here the contents of memory location whose address is specified in BX register are subtracted from 0 and the result will be stored in to the memory location. Negate in brackets SI. The contents of memory location whose address is specified in SI register will be subtracted with 0 and the result will be stored into the memory location. The next instructions is CMP, compare. This instruction will use to compare two operand values. It performs the subtraction of byte or word between the source and destination, and the result will not be stored, and it will reflect the flags. Here the syntax of the instruction is CMP destination comma source, where the destination can be a source or a memory location, and the source can be a memory location or register or an immediate data. For this instruction, both source and destination cannot be memory locations. The CM instruction will perform the subtraction of the source content from the destination. Based upon the result, it is going to affect the flags. So here, the destination contents are subtracted with the source contents. Based upon the result which is obtained after this subtraction, this will affect only the flags. The result will not be stored anywhere. The various flags it is going to affect is carry flag and zero flag. The cases where we can see here it is the destination and source may be greater, or destination may be less than source, or both source and destination are equal. Suppose if the destination is greater than source, in this subtraction the result is a positive quality, so no need of any carry or borrow, so carry flag is equal to 0. If the destination is less than source, that means the destination as it is a lesser value than source, you require a borrow here. As borrow is needed here, it is going to reflect the carry flag. If both the source and destination contents are same, the result is 0, which is going to affect the jet flag as 1. The jet flag as 1. The various flags will be affected mainly are auxiliary flag, carry flag, overflow flag, parity flag, sign flag, and zero flag. Few example for compare instruction are CMP AL comma BL. So this instruction will compare the AL register contents with the BL register contents. Based upon comparison, the flags may be affected. The flags which we can see is carry flag and zero flag. CMP CL comma 14H. So it will compare CL and 14H. Compare memory location contents with AL. So the memory location contents whose address is specified in BX registers are compared with AL register and will affect the carry and zero flags. Compare BX comma SI. So here the BX register contents are compared with the memory location contents whose address is specified in SI register. Based upon the result, this will affect the carry flags and zero flags. The next instruction is AAS, which stands for Ascii Adjust after subtraction. This instruction is used to adjust ASCII codes after subtraction. The AAS instruction we have to perform after subtraction instruction only. The syntax of the instruction is AAS. The functionality is, it is for adjusting the result of the subtraction of two packed BCD values to create a unpacked BCD result. In this instruction, the register AL is implied source and destination. The source and destination. The flags will be affected are auxiliary flag and carry flag. Example, move AL comma 41H, sub AL comma 49H. 49 will be subtracted with from 41H, which is going to result CCH. If you perform AAS instruction, the AL contents will be changed to 06H. Now we will see how this AAA instruction will work. The various steps which it is going to take is, first clear the upper nibble of AL register, then examine lower nibble of AL register. If the lower nibble of AL register is not a valid BCD number, that is greater than 9, then subtract 06 to AL and decrement AH register. If the lower nibble of AL register is a valid BCD number, that is less than or equivalent to 9, then no changes for both the registers AL and AH register. Now we will see with a few example how this AAS instruction will work. Let us assume after subtraction the difference are moved to AL register, which is equivalent to 6CH. So the AL register contents are 6CH. The instruction AAS, first it will clear the upper nibble of the AL register. So 6 will be cleared, which is going to result the AL register content is equivalent to 0CH. Then examine the lower nibble of AL register. The lower nibble of AL register in this example is C, which is not a valid BCD number as it is greater than 9. We have to subtract 06 from this contents. So that means AL register contents is equivalent to 06, 0C, from which we are going to be subtract 06. C minus 6. C in decimal is 12. 12 minus 6, 6, 0. Now the AL register content is equivalent to 06H. The next instruction is assuming after subtraction the AL register content is equivalent to 69H. First step, we have to clear the upper nibble. In this case it is 6 will be cleared. Now after this instruction the AL register content is equivalent to 09H. Then examine lower nibble. As it is a valid BCD number, as it is less than or equivalent to 9, don't alter the AL register contents. So you'll get the result as 09H after AAS instruction. The next example will take as AL is equivalent to D9H. In the first step, we have to clear the upper nibble. So D will be cleared to 0. So after the first step, AL register content is equivalent to 09H. In the second step, examine the lower nibble of AL register. In this case, as it is a valid BCD number which is less than or equivalent to 9, don't alter the content. So the result is 09H after AAS instruction. Last example will take after subtraction. Assume AL register content is equivalent to ABH. First we have to clear the upper nibble. So now in this example the upper nibble is A, that will be cleared. So after first step we will get AL register content is equivalent to 0BH. Then examine the lower nibble. In this case the lower nibble is B, which is not a valid BCD number as it is greater than 9. Subtract 6 from this content. B minus 6. B is 11. 11 minus 6, 5 will get. So after executing the AAS instruction, we will get AL contents as 05H. The next instruction will move to DAS instruction. DAS stands for decimal adjust after subtraction. This instruction also we have to perform after subtraction instruction. This instruction syntax is DAS, which is a 0 operand instruction. Here AL register is the implicit operand. The DAS instruction functionality is this adjusts the result of the subtraction of two packed BCD values to create a valid unpacked BCD result. AL register is the implied source and destination operand for this instruction. The flags affected are auxiliary flag and carry flag. Example, move AL, 75H, sub AL, 46H. What are the result which is obtained? That if you given for DAS instruction, it will be converted into 29H. Now we will see how this DAS instruction will work. The steps it is going to be checked is, first examine the lower nibble of AL register. If the lower nibble of AL register is not a valid BCD number, that is AL is greater than 9, then subtract 6 from the AL register. After the first step, check the upper nibble of AL register. If the upper nibble of AL register is not a valid BCD number, that is AL is greater than 9, then subtract 60 from AL register. In the two steps, if AL register nibble, whichever you are checking, if it is a valid BCD number that is greater than or less than or equivalent to 9, then don't alter the contents of AL register. Now we will illustrate with respect to few example. Let us assume after subtraction, the result which is there in AL register is 6CH. Now we will see how the DAS instruction will work for this case. So the AL register content in this case is 6CH. First step, we have to examine the lower nibble. In this case, the lower nibble is C, which is not a valid BCD number as it is greater than 9. So we have to subtract 06 from AL register contents, that is 6CH minus 06. C minus 6. C, it is equivalent to decimal is 12. 12 minus 6 is 6. 6 minus 0 is 6. So after this, AL register content is equivalent to 66H. Then we have to examine the upper nibble. In this example, the upper nibble is a valid BCD number as it is less than or equivalent to 9. So no need to alter any register contents. So after DAS instruction for this case, the result is 66H that we can see in AL register. We will move to the next example where we are assuming after subtraction, the AL register content is equivalent to 69H. Now we will see how this DAS instruction will work. So first step, we have to take AL register. First we have to examine lower nibble. In this case, 9 is the lower nibble, which is a valid BCD number as it is less than or equivalent to 9 condition is satisfied. So don't alter the contents of AL register. So this AL register contents are unchanged after first step. Then we have to take the AL register contents for examine the upper 4 bits, upper nibble. As in this case, the upper nibble is 6, which is a valid BCD number as it is less than or equivalent to 9. Don't alter the contents of AL register. So after DAS instruction, the contents of AL register is equivalent to 69H. Now we will see the illustration with respect to one more example. Let us assume after subtraction, the AL register content is D9H. Now we will see how this DAS instruction function for this case. So first I am taking the AL register contents as D9H. In the first step, we have to examine the lower 4 bits, that is lower nibble. In this example, as the lower nibble is a valid BCD number as it is less than or equivalent to 9, don't alter the contents of AL register. So it is going to be remains as D9H. In the second step, we have to take again AL register contents for examine the upper nibble. In this, the upper nibble is D, which is not a valid BCD number as this digit is greater than 9. So we have to subtract 60 from AL register. 9 minus 0, we get 9. D minus 6. D in decimal equivalent is 13. 13 minus 6 will get us 79. So after DAS instruction, the AL register content is 79H for this example. The last instruction we will see for DAS instruction, assuming after subtraction, the AL register content is equivalent to ABH. Now we will see how this DAS instruction will work for this case. So first we are taking AL register content is ABH. First we have to examine the lower nibble. In this case it is B as it is not a valid BCD number because B is greater than 9. We have to subtract 06 from AL register contents. It is a hexadecimal subtraction. B minus 6. In the decimal, we can write as B is equivalent to 11. 11 minus 6 is 5. A minus 0 is A. So after the first step, the result in AL register is A5 step. Now we will move to the second step. In the second step, we are going to examine the upper nibble. In this example, as the upper nibble is not a valid BCD number because A is greater than 9, so we have to subtract 60 from AL register. After subtracting 60 from this, 5 minus 0 get us 5. A minus 6, which is hexadecimal subtraction. A decimal equivalent is 10. 10 minus 6 will get us 44. So after EDAS instruction, the AL register contents is 45H in this example. With this, I conclude for today's session. Today we are discussed the instructions related to 8086 pertaining to arithmetic, that is exclusively addition and subtraction instruction. The various instructions which you are discussed in the today's session is add along with carry, increment, Ascii adjust after addition, decimal adjust after addition, subtraction SUB, subtraction with borrow SBB, decrement DEC, compare instruction CMP, negate instruction NEG, Ascii adjust after subtraction AAS, decimal adjust after subtraction DAS. Thank you. Next we will see multiplication, division along with the logical instruction in the next session. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.